Hacktex Virtual Training Materials. Advanced Textiles Manufacturing Industry. Learning Unit 5. Issues related to the sustainability of functional and smart textiles. Lesson 3. Eco-design for smart textiles. In this lesson, you will learn about the eco-design concept, eco-design strategies, life cycle assessment as a tool to characterize the environmental impacts of products. The life cycle of product can be simplified to this 5 phases: design, manufacturing, distribution, use, and end of life. The materials consumption, energy and resources use, release of hazardous substances, or waste generation, are mainly associated to the manufacturing, distribution, use, and end-of-life management phases of the product life cycle. However, it is estimated that over 80% of all product-related environmental impacts are determined during the design phase of a product. The growing awareness of the environmental degradation has focused the attention in eco-design. Eco-design is the process of designing products with environmental sustainability in mind. It involves considering the entire life cycle, from raw material extraction and production to use, disposal, and potential reuse or recycling. The goal of eco-design is to minimize the environmental impact of products and services while still meeting customer needs and maintaining profitability. The European Union has been at the forefront of promoting eco-design principles and policies. Some of these initiatives are the Eco-Design Directive or the Waste Framework Directive. In any case, the clear current position of the EU towards sustainable production clearly encourages the smart textile producers to develop their products under eco-design approaches. Eco-design strategies can be defined as techniques and approaches used to design products that reduce their environmental impact throughout their life cycle. In this section, some eco-design strategies, classified in this 4 categories, are analyzed. Considering minimum amount and diversity of materials that have the lowest possible impact can clearly set a difference to minimize the environmental impact of a smart textile. Since the production of a smart textile often implies the use of a large variety of non-renewable materials, it is key to reach optimal material efficiency by economizing the scarce raw materials application, using lightweight materials, avoiding excessive decorative layers, etc. When it is possible to find several alternatives for raw materials that can equally fulfill general requirements, it is necessary to establish eco-design criteria in the materials selection process to find those options that minimize the environmental impact, while considering all phases of the product lifecycle. As a general rule, reducing to a minimum the material diversity is necessary to also reduce the environmental impact of the product. The selection of raw materials for smart textiles must contain a wide diversity of criteria covering both performance, aesthetics, environmental, and other technical and manufacturing parameters. The manufacturing processes to be selected for the production of smart textiles are clearly connected to the raw materials to use and to the technologies to implement. The key points to consider from the eco-design point of view regarding the production phase involve minimization of production waste, reduction of production steps, and use of green, cleaner production processes. Because of their complexity, smart textiles present high economic and environmental costs. Due to this, extending their service life allows reaching a more sustainable production and avoids waste accumulation. To this end, it is necessary to ensure an appropriate durability of the smart textile as well as an intensive and controlled use of the product. The development of designs that consider the solution as a system of modules, rather than a whole integrated solution, can make them easier to customize and upgrade, but also to maintain and repair. Design for reparation involves considering that the products will need to be repaired or maintained at some point, and ensuring that these tasks can be carried out easily, quickly, and at a low cost, by using standardized components, designing products with accessible and visible fasteners, etc. Servitization is a business strategy rather than an eco-design strategy. Nonetheless, in servitization the company creates value for its customers, not by just selling them a product, but by offering a range of services around it, such as maintenance, repair, upgrades, etc. Given that the smart textile becomes the channel for providing the service, the company is the first interested to ensure its durability, good maintenance and, depending on the business model, its rotation, meaning that the product is more intensively used with an extended service life. Among all the available eco-design strategies for the end of life, the most interesting strategy for smart materials related to their last phase is the design for disassembly. Design for disassembly aims to make products that, at the end of their useful life, their parts can be easy to dismantle. Its goal is to minimize waste and environmental impact by making it easier to recover and reuse valuable resources from products, promoting the separation of the parts or components in order to ease their reuse, recycling or appropriate waste management route. The aim of using eco-design strategies during the development of a smart textile product is to reduce or minimize its environmental impact. However, the evaluation of these environmental impacts is not easy. What may seem a great solution to reduce an environmental impact can imply an increase of the environmental impact in other categories. Here lies the need to have tools for an objective evaluation. Tools that allow quantifying the impact in multiple categories, and comparing various alternatives to decide which is the best option, or if it is worth applying an eco-design strategy or not. The most widely used tool to perform such analysis is the life cycle assessment. Life cycle assessment, or LCA, is a methodology used to evaluate the environmental impacts of a product, service, or process throughout its entire life cycle, from raw material extraction and production, to use and disposal. LCA takes into account the environmental impact of all stages of a product's life cycle, including energy use, resource consumption, waste generation, and emissions to air, water, and soil. The LCA process typically involves four main steps. First, the goal and scope definition, which means establishing the product system boundaries, functional unit, and the environmental impact categories to be assessed. Second, the inventory analysis, that involves gathering data on the inputs, outputs, and emissions. Third, the impact assessment, which consists on evaluating the potential environmental impacts using established impact categories. And finally, the interpretation of the results, being all steps interdependent between them. Through these steps, LCA can reach a comprehensive evaluation of the environmental impacts considering multiple impact categories, allowing the identification of potential improvement opportunities in terms of the environmental performance, and providing a quantitative basis for comparing the environmental performance of different products or processes. LCA can be a complex process that requires specialized expertise and knowledge in environmental science, statistics, and modeling. Data collection is the most time and resource-consuming step of LCA, although it is a key step for performing good LCAs. Due to this, LCAs are often limited in scope. Other drawbacks of LCA are the difficulty to compare results across different studies and that there is a certain risk of misinterpretation or inappropriate use of the achieved results, which can lead to incorrect conclusions or misguided decision-making. Nonetheless, the overall balance points LCA as a valuable tool for evaluating the environmental performance of products and processes with the aim of identifying opportunities for improvement. Its transparency can help build trust and credibility with stakeholders, such as customers, regulators, and investors. The results of LCA studies on smart textiles suggest that the environmental impact of these products is highly dependent on the product and function itself, related to the specific technology and materials used, as well as the production and use patterns. However, LCA studies can provide valuable insights into the environmental performance of smart textiles, and inform the development of more sustainable products and processes. In this lesson you have reviewed the concept of ecodesign and its relevance towards the development of sustainable smart textiles. The overall ecodesign strategies that can be applied in the 5 main phases of the product's life cycle, focusing on some of the strategies that can be more suitable for smart textiles, owing their nature. And the LCA methodology as a tool to quantify and characterize the environmental impacts of smart textiles.